Okay, so today we'll discuss section 15.1 antiderivatives. So far we've only discussed the derivative. From this point onward, we're going to work backwards to find what's called the antiderivative, which is also called the indefinite integral. Here we're making the sometimes difficult leap between derivatives and their opposite, antiderivatives. You have to first be proficient at finding derivatives in order to find antiderivatives. Working in reverse is not always as easy as finding derivatives. So, let's start with an example. So we're starting down here. And I'm going to quiz you about this. If the derivative of f of x is given as f prime of x is equal to 2x, what function did it come from? What function has 2x as its derivative? Hopefully, x squared is what came to mind. This is called an antiderivative of f prime of x. So f of x, without the apostrophe, without the prime, is an antiderivative of f prime of x. So now instead of looking at the notation for the derivative, we're working backwards to find the antiderivative. Welcome to section 15.1, antiderivatives. This is a whole new topic. Thus far, we've only discussed the derivative. From this point onward, we will work backwards, beginning with the derivative, to find what's called the antiderivative, or also called the indefinite integral. Here we're making the sometimes difficult leap between derivatives and antiderivatives. Being proficient at finding antiderivatives requires very good skill at finding derivatives. Working in reverse is not always as easy as finding the derivative. So we'll discuss a bunch of rules on how to find their antiderivative. But let's begin with an example. If the derivative of f of x is given as f prime of x is equal to 2x, what is f of x? What function has 2x as its derivative? Hopefully, you thought of f of x equal to x squared. That's probably what came to mind. And that's true. So f of x, the original function, can be called an antiderivative of f prime of x. So this one has the apostrophe because it's the derivative, and this is the original function. So the original function can be thought of as the antiderivative of the derivative. Now, what about these following three functions? What is their derivative? The derivative of x squared plus 3 is 2x. The derivative of x squared minus 24 is also 2x. The derivative of x squared minus 3.5 is shockingly also 2x. So what does this lead us to conclude? Something that's a little bit weird, right? If I start off with the derivative being 2x, and I want you to tell me what function did it come from? So here I've got this 2x, and I want you to tell me what function it came from. Well, it could have come from x squared plus 3. Same derivative could have come from x squared minus 24. Same derivative could have come from x squared minus 35. It could have come from any of them. So we say that any function of the form, and I may not have the space to squeeze this in right here, so I'm going to try to put it above. Any function of the form x squared plus c would be considered an antiderivative of 2x. The unknown number represented by c is called an arbitrary constant. These antiderivatives, which include the c, are called general antiderivatives. Then there's this formal definition, which may confuse you a little bit. Don't let it put you off, because for some reason they like to use capital letters now to define the antiderivative. What's happening here is that you have a derivative, and there's that little apostrophe notation, but you could be given a derivative as its standalone function without the little tick mark. So to refer to the derivative, the antiderivative of that, they use a capital F instead of the apostrophe. So if the derivative of big F is little f, then big F is an antiderivative of little f, because it equals the derivative of big F. That's just the formal definition of it. But you have an intuitive understanding, because if you know how to find the derivative, the antiderivative is the function from which it came. So for example, let's verify, is big F the antiderivative of little f? What that would mean is that the derivative of big F should be little f. That's the question. Is the derivative of big F little f? Is that true? So if we find the derivative of big F and it's equivalent to little f, then that is the antiderivative. So the derivative of big F, you would keep the 1/2, and then you take the derivative of x cubed, which would be 3x squared. The derivative of any constant is 0, so this is 3 over 2x squared. Does that equal x squared? Are these equal? Nope. So big F is not the antiderivative of little f. Okay, I have to try to scroll down now, and I'm not sure if I'm going to be able to do this right. I want to scroll down, but I can't, I think, with the picture, with the written stuff here. So I may have to erase that so I can scroll down a little bit. So here, I can scroll down so you can see this, but now the writing is all off. So hopefully we wrote some of that down. So another way to represent the general antiderivative is by using what's called the indefinite integral. And this is where I start to generally lose people. So if little f of x is the derivative of big F of x, then, and actually listen to how I read this, this says the antiderivative of little f of x with respect to x is equal to capital F of x plus c. This all means just find the antiderivative of the small f of x, which happens to be big F. So the big F is the antiderivative of the little f. Continuing on. In that expression, the integral of f of x dx is called the indefinite integral of f of x. The elongated S-looking symbol is called an integral sign. F of x is called the integrand. Dx is called the differential and must be included in the integral. It tells us what variable the derivative is with respect to. So this is, for example, if you ever had a constant. So the antiderivative of 2. It might be 2x, it might be 2k, really hard to tell. So that d whatever is always there to let you know what the variable that we're using is supposed to be. The process of finding an antiderivative is called integration. So be aware, these two words are synonymous. Antiderivative and integration. I didn't mean to cross that out. They are synonymous. So, we'll now start with our first rule for integration. Integration is the reverse process of the derivative. For example, if f of x equals x to the fourth, the derivative would be, think about it, you know the answer to this, the derivative will be 4x to the third. The process by which we did that is the power rule that we learned for the derivative. You begin by multiplying by the exponent, and then you subtract 1 from the exponent. On the next slide, we'll attempt to figure out how to reverse the process. So literally, we will do the exact opposite of what we had just done. We multiply by the exponent and then we subtracted 1. So what would the reverse of that process be? It would be to add 1 to the exponent and then divide by the new exponent. So here it is. If you had 4x cubed, we want to work backwards to find its antiderivative. We know the answer. We know that the answer is x to the fourth. How do we know that? Because we just did this on this previous page. The derivative of x to the fourth is 4x cubed. But that's just because we know it. Is there a process by which we could figure that back out? Okay, so I had this written down and then I erased it. So this is x to the fourth. So again, if we literally reverse the process would be to add 1 to the power. So I'd keep my 4x cubed. Oops, I didn't mean to zoom that in. Oh, I went to the wrong page, sorry. I would add 1 to the power, so I keep my 4x cubed, add 1 to the power. That would give you 4x to the fourth. Actually, I don't want to do that. I want to actually write the notes in. You will add 1 to the power. That's where the fourth power comes from. And then you will divide by the new power. That's why the 4 is no longer there in the answer. That leads us to the power rule for integration, which is the counter to the power rule for differentiation, or finding the derivative. So if I am asking you to find the antiderivative of x to the nth power, the process is you add 1 to the power and then divide by that new power. Oh yeah, and don't forget to add this plus c. That's, again, the arbitrary constant, and it needs to always be there because we're not sure if the derivative 4x cubed came from plain old x to the fourth, back up here for this example, or if technically we had x to the fourth plus 2 or plus 7 or plus pi. We just don't know, so you always put the arbitrary constant in. So let's do some examples. Let's find the antiderivative of x to the negative 6. So to do that, remember what this is telling you. I'm going to point at it again. The integral sign is just instructions. Don't let it freak you out. It's telling you that you are finding the antiderivative. Of what? Of x to the negative 6 with x as the variable. So the only thing you are really looking at here is the thing in the middle. You're looking for the antiderivative of x to the negative 6. You can handle that. You just add 1 to the power and then divide by that new power. Don't forget to add c. So this is x to the negative 5 over negative 5 plus c. The next one is the antiderivative of the square root of x with respect to x. So some things never change. Just like when we took the derivative, the square root of x was not okay, nor is it okay in the antiderivative.